So let's get started. So in the last class, so let me do a quick recap of what we did in the last class. So I think we started looking at a few example problems. For example, the PCA was one example, and then we looked at various optimization problems that hopefully eventually we'll look at how to solve these. But these are the ways by which you can pose the optimization problems, right? Depending on the applications. So towards the end, we saw what is known as linear separation problem. Essentially, you have two data sets, and you have to separate it by a hyperplane. So all that you have to do is, basically, let's say you have one set of points like this and the other set of points like this. Then you have to separate it by a hyperplane that is quote unquote robust, right? What do you mean by robust? Because I can separate this by placing a hyperplane very close to, let's say, one of these points, right? In that case, when you deploy it in the field, because of noise, some points may lie to the right, in which case you will make a mistake, right? So you should optimally place, in the sense you should place it at the center, right? The question is, how do you pose that as an optimization problem? Essentially, what you have to do is find out the distance between the plane and the nearest point in one set, the plane and the nearest point in the other set. You try to maximize that distance, right? So essentially, what do you think is the solution? Can somebody guess? You have to place right in the middle, right? So that's the solution. So the question is, what should be the optimization problem for which you get this as a solution, right? We will see that maybe a little later. Okay, so today what we are going to do is we will start with optimization problem from today onwards. Okay, so how do you solve optimization problems? Okay, so let's start with some basic calculus, and then we will move on to I'll give you some sample optimization problem or a general form of optimization problems. And then we'll start with a very simple optimization problem called unconstrained optimization problem, and see how to solve those. Once we do that, then we will move on to constrained optimization problem, which is very relevant for most of the data analysis kind of applications. We will see how to solve such problems, right? So let's start with the some prelims. So let's look at a function. So typically, the kind of functions that we deal with will be a map from Rn to R. Right? Can you give me an example of a map from Rn to R? Huh? Norm, yes, good. Norm, inner products, right? Well, you fix one vector and take the other vector as x, right? X transpose v. So that's another example of a function, right? So you take a function. So now we know the notion of continuity of a function mapping from R to R. So what do you mean by continuity of such a function, right? So we say that f is continuous at x belonging to Rn. See, this x is a vector, okay, n-dimensional vector. We say that it's continuous at x if you take any sequence that converges to x, right? If for every xn converging to x. So what do you mean by xn converging to x? What do you mean by that? If you have a sequence of numbers, I say that xn converges to x, you know what it means, right? It will enter the epsilon room no matter what epsilon is after some time, right? That's what it means. Now, what do you mean by a sequence of vector xn converging to x? What do you mean by that? You should take an epsilon room around x. So what do you mean by an epsilon room around x? For scalars, epsilon room is essentially an interval around x, right? Of size epsilon by 2 on each side. So the total length is epsilon. So now what should I do here? You look at an epsilon ball around it, right? So you take a ball of size epsilon, that's my epsilon room. And you look at the sequence xn, which is a vector. Eventually that vector enters that room epsilon, right? Epsilon room. So you make epsilon very small, still the sequence will enter, perhaps after some time, right? So there is some delay, but it will still enter, right? An alternate way of saying this is, so you look at, for example, xn minus x, right? This is the difference. It's a vector, right? You look at the norm of this, okay? Well, it doesn't matter which norm you pick because of equivalence of norm. So let's take a 2 norm. And if you look at this, this is a sequence of number, right? For each n, xn minus x norm is a number, right? So you have a sequence of numbers, and I know what do you mean by this sequence of numbers going down to 0, right? So that sequence of number converges to 0 means you take an interval around 0, that epsilon room, it should enter, right? Okay, is this clear? Now we say that, so you take any sequence xn converges to x, then you look at f of xn. See, f of xn is a number, right? It's a sequence of numbers. So this should converge to f of x, right? So this is what you mean by continuity of a function f at xn. Okay. Now this is continuity of f. Now the second notion that we need in optimization is the derivative, right? So so let's look at the derivative of let f, you take a simple r to r itself, then how do you define df or dx? This is defined as, you look at f of x plus h, you look at f of x and divide by h, and then you take limit h tending to 0, right? So that is the definition of a derivative, right? This is a recap. I'm sure all of you know this. So if I want to extend this to Rn, so what should I do? So let's say let the function f Rn to R, then, so what should I do? Yeah, I really don't know. I cannot take x is a vector, add h is another vector, subtract f of x, and I cannot divide by h, right? So h is a vector. I don't know how to divide, right? What should I do? I will just perturb the ith component of the vector x. So what do you mean by that? Then I'll write it like this: x1, x2, this is xi, xn. Okay, I'm going to look at the ith component. What I'm going to do is I'm going to perturb the ith component by h, right? Just add a small, I'll just increase xi by h, right? And now I'll subtract this by xn, right? So essentially I'll take the ith component, I'll move slightly in the direction of ith component, see what is the function value, subtract f of xi, x1 through xn, divide by h. What is this? And I take the limit 1 to 0. So what is this? This is your partial derivative, right? So you take the derivative of the function with respect to the ith component, right? So this is what you have, right? So now I can do that for every direction I, x1, x2, x3, and so on, xn. I get n derivatives. I collect them and I call it as what? What is that called? What is that called? I'll do this, right? So I have f with respect to x1, f with respect to x2, and so on, f with respect to xn. What is this called? Huh? No idea. I mean, at least you would have seen this, right? What is this called? Huh? There's a name for this, right? I'm sure you would have studied this in your multivariable calculus or whatever, right? What is this called? Okay, I'll give extra 1 marks if you in the final. Huh? Okay, so You need such an incentive to answer, is it? Okay, so remind me towards the end. It's called the gradient, right? So gradient of f is, so I'll write this as, I'm going to use this symbol. Okay, this also belongs to Rn, right? It's a bunch of n vectors, right? This is a gradient, is also a vector. Okay, I know how to take the second derivative. So what is the second derivative of f of x1 through xn? How do I write the second derivative? Hmm? What is that called? Okay, you will get 1 mark provided you answer this. Then probably hope, Do you remember? Laplacian, no? Huh? Hessian, right? Yeah. So it's called the Hessian, right? So what is a Hessian? So essentially, there are n variables. I can take the second derivative with respect to each one of them. That gives me the diagonal, right? So dou f or dou x1, right? So you get the first derivative and so on. The second derivative, right? The sec of n xn, right? And then what about this second term? This is with respect to x1 and then with respect to x2, right? And so on. And similarly, you know how to fill this, right? This is called the Hessian, right? It's a n cross n matrix, right? Well, linear algebra will help us analyze these things. We'll see how to do that later on when we deal with what is known as convex functions, right? So essentially, the ijth entry of this is basically dou square f over dou xi dou xj. Okay, this is the ijth entry. Okay, so there is one more very, very important result. I'll just state this without proof. It follows from what is called the fundamental theorem of calculus. It's called the remainder form of Taylor series. You know what a Taylor series is, right? Everyone knows, right? F of x, you can expand it around a. You have f of a plus x minus a into f dash of a plus x minus a whole square, f double dash of a by 2 plus and so on, right? So there is something called remainder form of Taylor series. Can somebody tell me what is remainder form? I'll write the scalar version first. So for example, I'm looking at f of x. It's a mapping from R to R. I can write this as, I'll write it around a. F of a plus x minus a into f dash of a plus x minus a whole squared by 2 factorial into f double dash of a star for some a star in the domain of f. Okay, you know what the domain is, right? Set of all x which gets mapped under f, right? That is your domain. Okay, why is this true? Any idea? Can you guess why is it true? Well, I'll pictorially show it for the first order, not the second order. So let's say you have a function which maps, let's say this is your function, okay? Let's call this is let's say I'll call it as capital A and capital B. This is your function f, x. So what is the domain of this function? Can somebody tell me? What is the domain of this function? A to B, right? So now I want to look at a point, let's say somewhere here, okay? This is x. I want to see what is f of x, right? How do I write f of x? Well, let's look at I can draw a line like this, right? What is the slope of this line? Slope of this line. Hmm? See, you just look at the height, right? What is the height? This height is f of x minus f of a, right? So this is the height. What is the width? X minus a. If I take the ratio, I'll get the slope, right? Okay. So let me write that f of x minus f of a divided by x minus a is the slope. But now intuitively you can see that I can match this slope by drawing a tangent somewhere here, right? Do you agree? There is a tangent. So what is this point? This point is some a star, right? A star is between a and b. That means it's in the domain of the function. So if you look at the gradient at that point, that is f dash of a star, then I can write this as f of x minus f of a divided by x minus a, right? So I can write by cross multiplying, I can write f of x as f of a plus x minus a into f dash of a star, right? I can extend that to get this, okay? So you can extend beyond this also, but this is how you get your remainder form. By the way, you should note that this is exact equality. It's not less than or equal to, greater than or equal to, or approximately equal to. It's exact equal to. Okay. So now how do you extend this to, let's say, higher dimension? Can somebody tell me what is f of x? Well, this is true under certain conditions. It's not true for every function. It should be twice function. I can write this. So now what is the remainder form? Let's say f of x for every x in Rn. Well, I should always refer to the domain of f, but let's assume that the domain itself is Rn. Then f of x is, of course, I can, let me consider a point y instead of a. Okay, so f of y plus x minus y. Remember, this is a vector now, it's not a scalar. I have to take the transpose. All the vectors, I'm going to write it as column vectors, right? So I take the transpose, it becomes rho multiplied by the gradient of the function evaluated at y. Okay, I'm going to take the gradient and evaluate the gradient at y. So that's what we get. Plus, this will be x minus y transpose multiplied by the Hessian multiplied by x minus y. So you'll get a number, right? X minus y transpose is a row vector, H is a matrix, so it's 1 by n times n by n, so it will be 1 by n, right? You get one row and n columns, so you'll get another row vector. When you multiply by x minus y, which is a column vector, right? So row vector times column vector, you'll get a number, right? Of course, there is a by 2. Well, what is the issue here? I'll write it as H star, okay, where H star is the Hessian. So let me go back here. So this is f dash of a star. A star is some, so I'm going to take the second derivative, evaluate it at a star. What is a star? Nobody knows. I mean, it's some point in the domain of the function. So similarly here, a star is the Hessian evaluated at some, let me call this as x star, okay, belonging to domain of f. Is that fine? So you guys remember this, right? You agree? Is that okay? Fine. Okay, let's look at a few things. Okay, so some few observations which will be useful when we look at the algorithm and its analysis, right? Even a simple algorithm like gradient descent, right? So how do you analyze gradient descent? So let's look at suppose the Hessian of a function f is positive semi-definite. Okay, so what does that mean? If it's positive semi-definite, what does that mean? The eigenvalues are all non-negative, right? It's greater than or equal to 0. Then let's look at what is it that you can, let's say x transpose Hessian x. What can you say about this? Can somebody tell me what is the, huh? Huh? Greater than or equal to? Okay, so that's one thing. Anything else? Okay, so now the moment you say greater than or equal to 0, what can you say about x minus y transpose h star x minus y by 2? Definitely greater than or equal to 0. So if I drop this term, what do I get? See, left hand side I'm reducing, right hand side I'm reducing, right, by dropping it. So that means f of x is greater than or equal to, this implies f of x is greater than or equal to f of y plus x minus y transpose gradient of f evaluated at y. Right? You get this inequality, right? Do you agree? Is that clear? Fine. Okay. Okay. Let's look at this is one observation. So suppose the minimum eigenvalue of the Hessian is lambda min. Then of course it is lambda min greater than 0. Okay, so that means it has a non-zero eigenvalues, strictly positive, right? So then what can you say about this thing, x transpose hx? In fact, h is h star also, right? Because it doesn't matter at what point you are evaluating Hessian. This is true for all. The Hessian is the minimum eigenvalue of the Hessian is lambda min greater than 0. This is irrespective of the points that you pick in the domain. You pick any point, it's always greater than lambda min, and it's positive definite. Basically, I'm saying it's positive definite. Then what can you say about this? Okay, I can do this, right? So x transpose hx divided by, I can divide by norm squared. Do you agree? I can multiply and divide by norm squared. Okay, now I can write this as norm squared times v transpose hv, where v I'm going to write it as x by norm of x. Do you agree? This is simple algebra, right? X by norm of x and x by norm of x, it will be norm x whole squared. I get back this, right? So what can you say about this vector v? V is a unit vector. Okay. So now, what can you say about v transpose hv? So v transpose hv, what can I say about this one? What is the value of, so what is the least possible value that v transpose hv can take? Huh? Why is that? Because I can choose v to be the eigenvector corresponding to the least eigenvalue, right? So you'll get lambda min. If you choose any other vector, it will have a component in the direction of other eigenvectors, which is larger than lambda min, right? So you can verify that. So this is greater than or equal to lambda min. So what do I get here? So this will be greater than or equal to norm of h squared times lambda min, right? So therefore, this implies x transpose hx is greater than or equal to lambda min times norm of x squared, right? Fine. So then using this, what can you say about f of x? f of x is greater than or equal to f of y plus x minus y transpose gradient of f at y plus lambda min by 2 norm of x squared. Really nice result, right? So now I get a lower bound. And similarly, I can also get upper bound. How? If I say that the Hessian, the max eigenvalue is lambda max, I can get also, I'll write that f of x is less than or equal to f of y plus x minus y transpose gradient of f at y plus lambda max by 2 norm x squared. Provided, right, the max eigenvalue is lambda max, right? So provided the max eigenvalue of h is lambda max for all points in the domain of x. Okay, sorry, domain of f. Okay, so keep these inequalities in mind. Okay, so it's quite useful when we look at what is called convex functions or concave functions. It'll be very, very useful. Okay, so any questions? I'll pause for a minute and then any questions so far? Linear algebra is quite useful even here, right? So okay, shall we move on? No questions? No questions? Okay. I think this much of calculus is good enough for now. Let's move on to optimization. Okay, so a general optimization problem looks like this. Okay, so you have let f be some function from Rn to R, gi be some function from Rn to R. Okay, I equal to 1 to n, and some hi again Rn to R. I'll call it as j equal to 1 to m. You have these functions. So how does a general optimization problem looks like? So you have this, you minimize overall x, f of x is a number. Okay, so f is a mapping from Rn to R, subject to, you cannot choose any x, right? Subject to, there are certain constraints. What are those constraints? First constraint is gi of x less than or equal to 0. See, gi of x is less than or equal to 0 for every I equal to, so there are n constraints. Okay, and j of x equal to 0, j is 1 to m. So there are totally m plus n constraint and one objective. So this is called the objective function. Okay, these are called constraints set. These are called constraints. Okay, these are called constraints. Right? This is very too general, right? So many of the optimization problems that you will end up solving will have one or at most two constraints and one objective. Okay, but there are problems wherein you will have many more constraints, but mostly it will be 2, 3, whatever. Okay, so now let's look at a few things. So I have to pick an x that minimizes f of x, but I cannot choose any x, right? I have to choose x from set of all x such that gi of x is less than or equal to 0 and hj of x is equal to 0, right? So let me write that constraint set. So constraint set. So how does this look like? So this constraint set looks like uh, it's something like this, right? Set of all x in Rn such that gi of x is less than or equal to 0, I equal to 1 to n, and hi of x, j of x equal to 0, j equal to 1 to m. So any questions? Remember, gi of x is less than or equal to 0. You might be wondering, what about greater than or equal to 0? I'll just take minus, right? I'll call gi as minus gi. So everything. Equality is something that you need. Well, equality, I can write it as 2 a less than or equal to b and a greater than or equal to b implies a equal to b. So, or I can write instead of either I have to write this, or I can write greater than or equal to 0. That is also fine, because greater than or equal to 0, less than or equal to 0 will be equal to 0, right? Fine. One of them. So you have a constraint set, right? So for example, in 2 dimensions, let's say if I plot it like this, right? So this is your 2 dimension, and the constraint set could be like this, right? So this is your constraint set, right? It lies in, let's say, R2. So this is your function f of x1 comma x2, and this is x1, this is x2, and this is your constraint set S, and you have a function. I don't know how to write, but I'll try my best. Okay, you understood, right? So it's like a tent or something, and you have a set here, right? That's what I have written here. Okay, so now you need to understand 2 things, right? So one is, first of all, these sets, right, called constraint sets. So if you have, weird constraint sets, it's always difficult to optimize over that set, right? So if those constraint sets are nice, whatever nice means, then it will become easier, right? We will look at one set of nice constraint set, right, or a general class of nice constraint sets. Those are called convex sets, right? So what are convex sets? For example, uh, let me give you an example here. So this is a convex set. Why? How do you define a convex set? Any, have you studied convex sets in other courses? Yes or no? No. Okay. So what is a convex set? You know what a convex lens is, right? So essentially, the way to define this is, you take any 2 points, right? Any 2 points. You draw a line between them, right? All the points on the line should also belong to that set. Then we say that it's a convex set. So by the way, when I say convex set, all the points inside is all, you collect all the points inside this shape, right? For example, if you have like this, right? Is this a convex set? No. Why? If I take, for example, this point and this point, then if I look at the line joining, all the points here lie outside the set. Therefore, it is not convex, right? That's pretty easy to visualize. So now, in order to define this mathematically, I need to define, what do you mean by line joining between 2 points, or the set of all points connecting the 2 points, or 2 vectors in general, right? So let's look at that. Let's say you have 2 vectors here. So I'll write it in 2 dimensions. This is true for any dimension. So let me call this as x1, and there is another vector x2, right? I want to define all the points joining these 2 vectors, right? X1, or points x1 and x2, right? That means, suppose I want to, let's say, define this point here. How do you define this point? Any idea? How do you reach that point? First, you start from 0, go to x1, right? I go to x1, and then what do I do? If I go in the direction of x2 minus x1, so what is this vector? This is x2 minus x1, right? So if I go to x1 and then move along the direction of x2 minus x1, I go to x2, right? X1 cancels and I go. But I should not I should not travel a distance equal to norm of x2 minus x1. I should go by something smaller than that, right? So this point will be, I should move in the direction of x2 minus x1, but not totally. I should go by a fraction of distance, right? Let me use the fraction lambda. So what is this lambda? Any number between 0 and 1. If I say 0, I'll stop at x1. If I say 1, I'll stop at x2. If I take something between 0 and 1, I'll be on this line. Do you agree? So what do you think is this line now? This point, I have to add x1 also, right? I have to go to x1 and then move in the direction of x2 minus x1 by a fraction of a distance, right? So how do I write this? How do I write this? So I can write this as follows, right? So I have lambda x2 plus 1 minus lambda x1, right? Algebraic manipulation. I have done nothing fancy here, okay? I've taken out x1 common. I'll get 1 minus lambda out and then lambda times x2. Or I can also write lambda x1 plus 1 minus lambda x2, right? It doesn't matter, okay? So now this leads to the definition, right? So a line connecting 2 points x, y belonging to Rn is defined as, how do I write this? It is all those points, I'll lambda x plus 1 minus lambda y such that I vary lambda, right? So lambda belongs to 0, 1. So this gives me the line, okay? And this defines all the points on the line. That's all. Now, how do you define convex sets? You take any 2 points in the convex set and you draw a line, or any points on the line should belong to the set, right? That's easy. So how do you write that? This is important. Convex set. A set, I'll take a set C which is a subset of Rn, okay, in general. Whatever I have shown previously, for example, this and this is not a convex function, the convex set. This is a convex set, so I've written it on a plane, so it's a subset of R2, right? And in general, I can take a subset of Rn, right? Is said to be a convex set if you take any 2 points, right? If for every xy belonging to set C implies lambda x plus 1 minus lambda y, right? For a fixed lambda, this gives me a point on the line joining between the 2 points x and y, right? This should also belong to C. For all lambda in 0 and 1. Right? That's all. I mean, just convert your geometry into math, that will give you this definition, right? So let's look at a few examples, right? So now I have to look at a few examples, otherwise it doesn't make sense. Now let's look at a ball in Rn. So do you think a sphere in Rn or a ball in Rn is a convex set? Yes, right? You take any 2 points, yeah. Does it matter which ball you pick? When I say which ball, ball is defined as what? I should use norm to define ball, right? If you use 2 norm, I'll get the usual ball. But if I use some other norm, I'll get different shapes, right? Do you think it depends on the norm that I pick? Huh? No. Why? Okay, so we'll see, right? So let's say ball at 0 and radius r, which is defined as all the points x in Rn such that norm of x I'm not specifying any norm here. It can be any norm in Rn, right? Is less than or equal to R. For example, if you pick one norm, you will get this kind of a shape, right? So you won't get a circle. If you take two norm, then you get a usual is convex. So how do you prove that? You take 2 points, right? Take x, y belonging to. Let's see if we can prove this easily. You take these 2 points. Now I have to draw a line joining between this. So what does this imply? This implies norm of x is less than or equal to r. Norm of y is less than or equal to r. That's what this set says, right? The moment you say it belongs to this, it's within r distance from the origin. Now, what is it that I have to prove? I have to prove that all the points on the line, right, belong to this set. So let's look at this. Lambda x plus 1 minus lambda y belongs to this ball, right? Is the question, right? We need to answer this. So when do you say that it belongs to the ball? If the norm of that is less than or equal to r, right? That's what we have to verify. So we'll verify that lambda x plus 1 minus lambda y norm, any norm. I have to show that this is less than or equal to r. So how do I show that? How should we show that this is less than or equal to r? Huh? Sorry? Triangular inequality, because it's true for any norm, right? I need not worry about which norm. So I'll have norm of x plus y is less than or equal to norm of x plus norm of y. Okay. Remember, lambda is a scalar and x is a vector. Plus. So what is the next step? Norm of lambda x is what? Huh? I can write this as. Can I do that all the time? Huh? Norm of alpha x is mod of alpha times norm of x, right? It scales by alpha. So do I need mod lambda? No, because lambda is, yeah, it's between 0 and 1. So this is lambda norm of x plus 1 minus lambda norm of y. Okay, what is the next step? I know that x belongs to the ball, y belongs to the ball. What does that imply? This, right? Norm of x is less than or equal to r and norm of y is less than or equal to r, right? So lambda times, I'll replace norm of x by r plus 1 minus lambda times norm of this, which is equal to r, right? So this is triangle inequality, right? And this is as usual. So the rest follows. Is that fine? So it doesn't matter which ball you pick, it corresponds to a convex set. Okay. Anything else? Anything else? Okay. So there are many other sets which correspond to which gives us a convex set. We will see many more such sets as we move forward. Okay. Now let me give you one more example, but this is definitely convex, but it is much more than convex. Let's look at this. What is this? You remember the symbol? What is this? Huh? Set of all n cross n symmetric positive definite matrices, right? Yeah. So is convex. Is it convex? How do you prove that? So take two, of course, I have to take 2 points in the set. Now points correspond to matrices. So you take A and B belonging to S plus N. Okay. Right? So this implies what? This implies A is A transpose, B is B transpose, and A, B both are positive definite. Right? This is what it implies. Now I have to take a line, right? So what do you mean by line here? Can somebody tell me what is a line? Joining the two matrices A, B? Well, quote unquote line, right? What is that? What is that? Set of all? What do you mean by set of all matrices between A and B? What do you mean by in between? That's not guaranteed, right? All the time. No, what did we do? You just have to mimic this, right? What did we do here? We took 2 points in C. C could be anything, right? It could be Sn plus plus or it could be something else. I took 2 points. In my case, in the current situation, I have taken two matrices. And what is the line? It's lambda x plus 1 minus lambda y, right? What should I do here? Same thing. Lambda A plus 1 minus lambda B. Obviously, this is symmetric, right? So lambda is between 0 1, okay? So this is symmetric. Okay. Of course, I'll write lambda between 0 and 1. This is clear, right? What else I have to show? It's obviously n cross n. I have to show that this is positive, positive definite, right? In this case, how do you prove that? You take x transpose lambda. So you take this matrix. I have to show that this is greater than 0 for every x, right? This is the definition of positive definiteness. Greater than 0, not greater than or equal to. So how do you show this? Huh? So this implies what? I mean, yeah, I can write this as x transpose. I'll pull lambda out, ax plus 1 minus lambda times x transpose bx, right? Well, x transpose ax is always greater than 0, right? Because a is positive definite. X transpose bx is always greater than 0 for every x because b is positive definite. So I'm taking what is called convex combination, right? Lambda times something positive plus 1 minus lambda something positive is strictly greater than 0. Do you agree? So it is convex. Well, interestingly, it's more than convex. Let's see other geometries. That's why geometry helps, right? So, do you know what a cone is? What is a cone? How do you define cone? Okay, let's look at ice cream cone, right? So this is your ice cream cone. How do you define? Well, all the points here, right? So that's an ice cream cone. Well, you take an infinite ice cream cone, not truncated, right? So how do you define this cone? Think geometry. I mean, right? High school. So how do you define this? What are the characteristics of this cone? Huh? How do you define this cone? Huh? Yes. How do you define this cone? You take a point, right? Well, let me start at origin. Okay, so this is origin. If you take a point, that's a vector, right? Now, I can scale it by any number, right? For example, I scale it by huge number, it goes here. That vector is also there in the set. Do you agree? Huh? Do you agree with that? So no matter what point you pick this point, yeah, you take this, you scale it by any non-negative number. Of course, you can scale it down also. Let's say you multiply by half, it will come down, but still it's there in the set, right? That's how you define a cone, right? So let's define that. So definition: a set C, of course, a subset of Rn is a cone if you take any for every x in C. What should I do? I should multiply it by a number. Okay, so alpha x also belongs to C for every alpha greater than or equal to 0, right? You scale it down or up, but you should not reverse the direction, right? You cannot multiply it by minus something, okay? That gives you a double-sided cone, right? So that's how you define double-sided. Now, interesting example is, what can I say about this again? Of course, this was convex. Definitely, this is convex set. Do you agree? Take any 2 points here and join them, you still get a point, right? So, okay. So now, do you think this is a cone? How do you prove that? Very easy. You take a point in the S plus plus n, that means a matrix. You scale it by a non-negative number. Of course, it was symmetric. Again, it remains symmetric. It was positive definite. It will remain as positive definite, right? Well, small catch here. If I use alpha greater than or equal to 0, if I put alpha equal to 0, it will not be there in the set, right? So this point is not there. So what do I do? I'll just remove this plus plus to 1 plus. That means it's a set of all symmetric positive semi-definite cone. It's a cone, right? Is that fine? So now, why do you need this? Well, thinking, so I can think of Sn plus as cone, right? So I can imagine now. I have some way of visualization. Otherwise, I don't know how to visualize S plus N, right? It's weird set. Now, why is it useful? There are certain problems. For example, I can say, okay, so those who know some very complicated things like this, okay? Uh, maximize overall sigma, sorry, such that sigma, I want this to be symmetric and I want it to be positive definite. Why? It's some power allocation. So power cannot be negative, right? So I can say that this belongs to, I can always do that. Well, this is maximization of some log det function, which is complicated. We will see such functions later, but subjected to a conic constraint, right? So I can think of each sigma belonging to a cone, right? There is one more constraint, which is I cannot use any cone. I can take the matrix to infinity and use infinite power. That doesn't make sense. So I want it to be less than or equal to some constant, let's say p. Okay, this is Frobenius now. Okay, uh, don't worry about this constraint. This will say that it should also belong to a circle. So what? How does this? See now, how do I visualize this? The first one says it belongs to a cone, right? This is how it looks like. Well, not exactly this, but this is how I can visualize. Frobenius norms less than or equal to p, or Frobenius norm squared less than or equal to p. What does that mean? That forms a ball, right? Circle. So it's like this. It is all the points here, right? This is how I can visualize. This is my constraint set. Right? At least I have the ability to view things now geometrically, right? Otherwise, this constraint set. I mean, have you ever imagined? I can think of it as actual ice cream, right? Well, not really. I mean, yeah, ice cream filled, cone filled with ice cream, right? So this is how it looks like, right? I mean, nobody could have imagined that. I can imagine this constraint set this way, right? Well, it has some use, not that you can just visualize. You can also use that visualization to come up with better algorithms and so on. Okay. Any questions so far? Right. So we have studied cone and we have studied convex sets. Right. So in the next class, we will see a few more examples, and we will see how to convert a non-convex to convex set. So for example, if you have this set, right, how do you convert this into convex set? Why do you need to do that? Well, it's difficult to deal with non-convex, right? I have to, convex is always nice. How do you do that? Huh? What do you do? All that I have to do, again, geometry, right? So I have to just do this, right? Join this line and fill this hole. Now this hole I have filled, and of course this was there before. Everything put together is a convex set. This is called convex hull. Okay, so you just fill the gaps and make it convex. That operation is called convex hull, right? Many a times, the reason why we do this is a very good approximation for convex sets. So hopefully, we can solve this problem. Then I can solve the original problem pretty accurately. Okay. So any questions? So I'll stop here. We have 2 more minutes. Any questions?